doing yesterday, and we just need to finish it to move on. And well, I want to start from a question. Just to take a pause, drink some coffee. This is a situation we call, please don't kill me. Or I'm leading you to a fire. And technically, you shouldn't think too long, because this is just a copy of a question from yesterday, for which the answer also was on the screen, because it's about relative motion. So, as we said, we can write many equations. This is the Doppler effect equation, but also we can relate speeds. For example, in this situation, this is the speed of the sound relative to the ground, and this is the speed of the observer relative to the ground. So the speed of the sound relative to the observer will be equal to the difference. I'm going to write it in a minute, but first, in general, just to review what it's based on. It's based on the fact that the velocity of the sound relative to the observer should be equal to the velocity of the sound relative to the ground plus the velocity of what relative to what. And if we go back in time, the rule was, we have three objects, the velocity of the third object relative to the first should be equal to the velocity of the third object relative to the second, plus the velocity of the second object relative to the first. This is a review, nothing new. And objects 1, 2, 3 can be chosen in any way. So in this situation, this is what we call sound. This is what we call observer. So automatically, the object number 2 becomes ground. So we should write here the velocity of the ground relative to the observer. And if we do vectors, an unknown vector should be equal to this plus, well, if velocity of the observer relative to the ground points to the right, that means velocity of the ground relative to the observer points to the left. So technically, that's what we're doing, a tail to a head rule. And this arrow represents, bless you, the velocity we're looking for. And now we can see that the magnitude of that arrow is equal to the difference between two magnitudes. And that is why, in the first place, based on what's happening to the distance, we said it's supposed to be equal to the velocity of the sound relative to the ground minus the speed, well, in this case, speed. Well, for the sound, speed and velocity don't make any difference. So speed, but it's better to get used to see the difference between velocities and speed. So minus speed of the observer relative to the ground. Okay, that's a review part. Now, Walter, what else can we write down? Well, again, I have no idea if the equations I'm writing will be helpful or not. I'm just writing everything I can. So relative to the observer, we can always write this equation. And this is that velocity or speed of the sound relative to the observer, the wavelength measured by the observer, and the frequency of the sound experienced, measured, heard by the observer in the actual case, or when everything is at rest, still same expressions. So 1, 2, 3, 4, and actually not all of them. We had more. For example, we also had a relationship between wavelength when the source was moving and then, well, the new wavelength. Well, in this situation, the wave shrinks, so the new wavelength should be shorter by the speed of the source divided by the frequency. Well, of course, we never need to use all of them, but we never know for sure which we should use. So it is, again, a good practice, just be able to write everything. Now, I go back to numbers. What do we know? Well, we know this, that the speed of the observer running on the ground relative to the ground. Truck, that the speed of the truck, which is the source relative to the ground. All right, these two numbers automatically tells us this is supposed to be equal to, what did we say, 340 minus 5, 335. By the way, I didn't write this number. That's supposed to be 340. And the observer finds that the truck makes a sound with this given wavelength. Okay, 0.5. What kind of a wavelength is that? This is a crucial point. It tests our understanding of what's happening. So we have two choices, either this or this. One choice is correct, second choice is wrong. We make a correct choice, everything else will be correct. We make a wrong choice, we make a mistake, and problem is not solved. So you should make your mind, cross one, circle another. And then you will live with this choice to the rest of your life, or at least to the Monday. I'm not going to ask you to do any pictures today, just make your mind. Just make your mind. So, if you think this is the correct choice, just wave your hand. This. If you think this is the correct choice, please wave your hand. All set. So we are ready. That's wrong. That's correct. So the observer finds we can actually write this as an equation number 6 if we want to. And again, we have more equations than we need. So, for example, the equation number 3 has two, as you know, variables right now. We know the speed of the sound relative to the observer, and we know the wavelength measured by the observer. So we don't really need, we could have used equation number 1 or others, but so I'm just going to add the equation number 3. That's 335. That's 0.5. So 670. And now actually we can go back to the equation number 1, because 670 is supposed to be equal to this, and that's supposed to be 340 minus, what was it, 5? And that's 340 minus 10. Which is 335. And we know why. And this is 330. So we can solve it for the original frequency, which would have been measured if nothing would have been moving. 670 over 335, 2, 660. And what was it, number 4? .52. Well, 1.5. I'm around it up. We have found everything. Yeah. All frequencies on all wavelengths. Any questions? Do you have a question? You should ask a question. Just ask a question. Any question. I will answer honestly. Can't hear you.
So I was asking her if the equation used
I used that number from equation 2. This is the speed of the sound relative to the observer. And I used this speed of the sound relative to the observer in the equation number 3, where everything is related to the observer. Prime, prime, prime means observer, observer, observer. And the equation number 3 becomes 335 equals 0.5 times the frequency of the sound experienced by the observer. If you ask, not always, but sometimes I do answer. Any questions? Well, we got like maybe 5 more slides related to sound. First, one more question. What do you think about this situation? And you should know the answer. We don't have to always travel slower than the sound travels. We can travel at the speed of the sound. We can travel faster than the speed of the sound. And every time we generate a specific set of waves. So those circles represent wave fronts generated at different locations of this source. And what is the right answer? as fast as the sound, right? So they travel together. The wavefronts travel with the source. So the answer is 2. Now, this is a very neat movie, very short. I recommend to watch it. And what is happening when a fighter jet, breaks the sound barrier? Kind of cool. But if you have a jet ski, you can actually do the same thing on a lake. If you have waves traveling on the surface, they have a certain speed to travel. So if you start traveling faster, you can see how you make the kind of, not a sonic boom, but water shock wave. Now, we know that in general, when we speak or when we listen to something, the distance matters. Only when a flat or plane wave travels in space, the amplitude of that wave, neglecting friction, internal friction, the amplitude of that plane wave, remains constant, and the intensity of the energy of the sound related to amplitude squared in any wave. But in real life, it's not a case usually, because when actual waves travel in all directions, even in an ideal situation, when there is no friction, no loss, total amount of energy traveling every second through each, sphere should be the same. So when the radius increases, the energy per meter squared should decrease. And that's what we call an intensity. For any wave, not just sound wave, this is a standard definition of intensity. It's the amount of energy traveling through 1 square meter every second, basically. That's what it is. And that's how our ear detects the sound, based on intensity of the sound wave. We know that in general, a sound wave is just a sequence of concentration and rarefaction above the average. And a regular human being, on average, can hear only certain frequencies within this particular range. Yeah. Dogs and bats, for example, they can hear much better. But what's interesting, this knob represents the amplitude. Did I turn it on? Oh, one more thing. You have to plug it in. So 8.46. Can you hear anything? No. So we have to go above a certain frequency. But more importantly, I don't change the amplitude, which means I don't change the energy output. The energy depends on how much current travels through the coils of this speaker. All I change is frequency. But for different frequencies, it sounds differently. Some louder, some not so loud. So our perception of sound actually is not directly proportional to energy, not to intensity. Well, that's the maximum, 10,000. I can't go higher. So we people, physicists, biologists, had to invent a variable which would describe our human perception of the sound. And that's what the loudness is. Yeah. So there is a physical quantity, intensity, related to the amount of energy traveling every second through 1 square meter. And there is a quantity which describes a perception of a sound by an average human being, loudness. And this is the way for calculating, for kind of translating the energy output into the loudness. This is a fixed intensity. This is the intensity of, minimum intensity needed for an average person to hear the sound at 1000 hertz. We call it a threshold of hearing. And different types of sound provide different types of energy. But if we convert it into loudness, it's a logarithmic scale, we can, normal conversation, 65 what? Well, we call it decibels. Well, you know who Bell is. He invented the phone. So this is like 10 bells. And the equation can be used both ways. And there is one question I want to ask you. What do you think about this situation? So you've been listening to a single speaker. And let's say you have that device I used the other day, which measures decibels. You can read, and you read 40. Then you place a second, like I also had in the past, and turn it on, identical, so exactly same tone, exactly same amplitude. So what do you think should happen to the perception, to the loudness? And I forget to check. Do you have an option, none of the above? All right, where is it? Here, resend. Nope. I don't want to close it. Okay, that's good. Now I want this. That's the equation. That's the question. Now let's see. 10. Number 9, supposed to be, did I check it? What happened to the Firefox? Four. All right. Well, what we had is this. So that was 40. So technically we could have calculated the intensity. But what we need to understand, when we add a second speaker identical, we don't double the loudness, we double the energy output. That's what we do. The amount of energy which being generated is doubled. So the new intensity will be twice of the old intensity. And now we just can calculate the new intensity, beta 2, 10 decibels times this is a common logarithm. The new intensity is this. And well, this is a part when we need to refresh a product of a log. What rule did I use? That's the rule I used. And my A is 2, and my B is that ratio. I just keep the whole ratio. And this is 40. And this is, well, at this time, we just got to take a calculator and calculate wherever it is. So this is just an illustration, a difference between the loudness and the intensity. Intensity is a physical variable related to the phenomenon, which we call making a sound. It doesn't depend on people, it doesn't depend on humans, it doesn't depend on location. It's going to be here on the earth or anywhere else where we have air. But the perception, our perception of sound, is not proportional to energy. It's logarithmic. So if we double the energy, it doesn't mean our perception also doubles. No. So this is just a mathematical illustration of how we humans perceive sounds. Where? Here. I'm ready. This is time for any questions. After that, we start the new topic according to the syllabus, which will not be a part of the exam, but still we have to use this time. Yes?
I didn't understand when we did the problem in class for the standing wave amplitude equals 6 millimeter, distance traveled by antinode of string in 1/4.
Distance traveled by antinode.
1/4 of a period.
Yes.
How did we approach that problem? I looked at the notes online and I still didn't understand what we did.
We imagined that we were so capable, so we could actually see how it's been moving. I remember this was third mode. And if we try to make a movie of the motion of a string with both ends fixed, and let's say this is a profile at t equals 0. The picture had shown several profiles. So my question to you now, how do you draw a profile of this string at t equals 1/4 of a period? That's exactly what the question is about. Each particle, each part of this wave travels. Some travel down, some travel up, because it starts from the maximum displacement for all. And these don't move at all, but these move with maximum amplitudes, antinodes. So if we wait exactly 1 period, what should we see? Well, now, please draw the picture of what you see in exactly 1 period and email it to me. This is a snapshot of a profile of a standing wave on a string at t equals 0 when all particles reach maximum displacement from equilibrium. In fact, they all instantaneously, momentarily stop. And then they start move. It's like a ball in a spring. They all start moving, well, some down, some up. Couple of points, 1 and 2, don't move at all. We call them nodes. But if we wait a certain time, the profile should change. So if you wait exactly 1/4 of a period, what should be your new profile look like? By the way, if we wait exactly 1 period, what does it mean? How should it look like? The same. That's what a period means. They all come back to the original location. So that's what we should see in exactly 1 period. And of course, we could ask a question, what should we see in a half of a period? In a half of a period, well, these points don't move. But in a half of a period, all other points should reach the location exactly opposite. That's what is happening in a half of a period. So in a half of a period, we should see this. They all reach again maximum displacement from equilibrium. They all again stop momentarily. So, but the question is, what should we see in 1/4? What do you see in 1/4? Yeah, here, that's the missing part. Because in 1/4 of a period, all particles should be brought back to the equilibrium. That's what equilibrium is. Yeah. There's not much of a difference between this type of a motion and the motion of each particle. So that's exactly 1 amplitude. And each particle travels different distance. This doesn't travel at all. This travels this distance. This travels the most of the distance. So from here to here, it travels 1 amplitude. So every antinode travels exactly 1 amplitude of a wave in exactly 1/4 of a period.
So on the slide, we had said that it was 3 millimeters. Why is it not 6 millimeters?
No, you read the slide wrong. The slide was saying 6 millimeters. 3 millimeters was the amplitude of traveling waves, which together, when overlapping, when interfering, would give the original wave. That was 6 millimeters. But we know that when a standing wave is generated, this is literally is superposition, overlapping addition of 2 individual traveling waves. So this amplitude A1, this amplitude A2 should be equal to this amplitude plus that amplitude. In all our examples, those amplitudes are equal to each other. So A will be equal to 2 times individual, or individual equals a half of the standing wave. That's what was happening. Different amplitudes, an actual standing wave and those traveling waves which together produce that standing wave. Please, next question. Yes.
This was a question on
Mm-hmm.
and there were plates around it that was keeping it from turning.
Okay, so in general, we need to see the difference between two equally important situations. Number one, only magnetic field acting on a particle. In that case, if it travels in a magnetic field, let's say, I don't know, positive, so the right-hand rule tells it should go, well, actually, I need more. So this is a standard representation. As you know, magnetic field points B into the screen, so it should start traveling in circles like this. And we know that in this situation, mv squared over r equals qvb, etc., everything can be found from that. A second different situation happening when we have two fields, B and E. So let's say we have the same B, and we're adding electric field normally to prevent particle from circling and just to make it move straight ahead. So in this situation, let's say the same particle, same charge, let's say it's positive, and I want to make it move just like this. So first, we know that's supposed to be magnetic force, Lorenz's force acting on it, and that's supposed to point like this, F magnetic. In order to make the particle travel with constant velocity straight ahead, we must cancel this force, which means we also should have electric force acting on it. And electric force should be opposite to the magnetic force and should have exactly the same magnitude. And in that case, velocity remains constant. And now we can just write this fact that the magnitude of the magnetic force should be equal to the magnitude of the electric force, QVB equals QE. This comes from exam 1. Turns out charge getting canceled, so this is when it might happen. And if this condition is not satisfied, the particle will travel along some bent trajectory. Did I answer? Okay. Please, yes. For direction of the electric field, I didn't write that equation, we should use an actual relationship between electric force, electric charge, and electric field vector. And this rule says when a charge is positive, well, in this situation, the electric field points in exactly the same direction as electric force points. If a charge is negative, electric field points in the opposite direction. Anyone? Question?
I just had a question about Lenz's force with the negative problem, and I always so I was wondering if you could just do an example.
I didn't understand the question. Could you be more specific, maybe related to some specific problem?
I think it was that how when you oppose loss, I think you have to.
Well,
So we did a problem where where it showed the EMF and the I, and how you get slope
So this is the Faraday's law, and we use the Faraday's law when we need to calculate something, EMF, because if we know EMF, we can calculate electric current. So, and we use this equation when we have information about flux or magnetic field in area. So in that situation, we draw graphs if we want to relate all these variables. Actually, let's start from the beginning. Magnetic flux is equal to magnetic field times area times the cosine of the angle between the area vector and magnetic field. So magnetic flux might change due to many different reasons. For example, magnetic field might increase or decrease. We can increase or decrease the area, or we can turn the loop. Okay, 5 more minutes. And let's say we do something and magnetic flux changes according to, I don't know, sine as a function of time. Normally it happens when we turn the loop. So slope, this is how we check the slope. We just draw several lines tangent to the graph. This means slope is positive. This means slope is negative. This means slope equals 0. And now we can sketch a graph for the slope. So it starts from certain value, then goes to 0, and remains positive, and then, so it should go like this. But that's not the EMF, because EMF is supposed to be opposite to that because of the negative n. So we just take this graph and we flip it. EMF should look like this. And that looks like a negative cosine, doesn't matter. So if we calculate current, that would give exactly the same graph because the resistance is positive. Now, no, just the same slide. The Lenz's law we use when we need to figure out the direction depends on what is happening. Let's say, again, just one example, magnetic field points relative to you into the screen and increases, or no, let's say decreases, because it's less obvious. So we should have less magnetic flux, but this is, again, the magnetic flux of the external magnetic field, and the change, we call it decrease. So, and we need to oppose the change, not the field. In that case, what we see is magnetic number of magnetic field lines gradually decreases. That's the change. So what we want to induce some more field with the same direction. So if this disappears, we're adding, this disappears, we're adding. So that slows down the change, which means in this particular situation, the induced magnetic field is supposed to point like the external points. And now finally we can use the rule which relates magnetic field and current which induces it. So that will be a loop, that will be the current. So electric current is induced by the change happening to the external field, but also this electric current induces magnetic field. So this magnetic field is induced by electric current, which is induced by the change happening to the external magnetic field. Yes?
Shouldn't the graph of EMF be on right now, as the slope of the flux is positive, so is the slope of EMF. And when the slope of the flux is positive, shouldn't the slope of the EMF be negative?
No. The Faraday's law says EMF equals negative n times slope. What you say is slope of EMF equals, but that's not the law Michael Faraday derived. You inventing your own law, and it's not the right way to do it. We are relating the actual instantaneous value of EMF and the slope of that quantity. There is no slope and slope relationship. There is a relationship between a value and the slope. And this, if the slope is positive, the actual value of EMF is supposed to be negative. The actual value. Yeah.
So if you were to increase the
One change here results in one change here. One change. What changes could happen? We can change the direction of the external magnetic field, but still keep it decreasing. In that case, we should change the direction of the induced magnetic field and current. Or we can keep the direction of magnetic field, but make it increase. In that case, we still have to change direction of this. One change there, one change here. You make two changes, so you get back to the same picture. Please ask a question. That's a punishment for being late. Any question? No, I'm going to wait. You have to ask a question. That's Faraday's law. All right, moving on. Any questions? Seriously? Well, we still have office hours, 2 more days, piazza, so. No. Yes. We start talking about light. And probably one of the most important physical matters for us humans, because 99% of information about everything comes through eyes. And people have been thinking about properties of light for actually thousands of years. And one of the question which people pondering with is, what is light? A set of particles traveling away from a source, or a wave like sound? And right now we know it's, well, depending on your philosophical view, now we know it's either both or neither, and people still debating how to call it. For me, it doesn't really matter. A light is a matter which sometimes shows property-like, particle-like properties, and sometimes shows wave-like properties. That's it. We just need to know when we should use which property. It's like person, but you look, in front of or side of the person, same person, but look differently. So the first theory of light, which helped to explain lots of things about it, was a particle theory of light. And it's not surprisingly, Sir Isaac Newton developed it. And after that, many years, decades, people thought light is composed of tiny particles which can travel away from a source, like tiny balls. For example, it's really easy to explain the development of shadow. tiny particles travel and just getting stuck. So that's why there is no light behind any solid object. But if it's something transparent, they can get through. That's it. And a trajectory of a single particle is supposed to be a straight line. It's not affected by anything. And that trajectory is called a ray or a beam. And the best way to represent light traveling from a source is using those rays or beams. So this projector right now shines on this screen, and we can imagine many beams go from the bulb and reach different locations of this screen. What's happening then? Well, like particles, some of them get stuck, some get reflected. So you don't look directly into the projector, no. You see the light reflected off the screen and traveling to your retina. And well, in this particular situation, the only color, not white color, you see is blue. Why? What do you say?
Not projecting a red color.
The regular incandescent bulb, which is inside that projector, but only more powerful, when you turn it on, is white because it produces light of all possible colors. White is not a specific color, it's a mixture of all possible colors. If you take a rainbow and then squeeze it together, that's going to be white. What's black? What does it mean? What do you think? Why is this black?
It absorbs.
It absorbs everything. So nothing is getting reflected of this. So, and why is it blue?
It reflects blue.
It reflects only blue. All other colors get absorbed by the screen. That's it. So, reflection and absorptions. One of the most important commonly happening phenomena with light. Well, in general, this tabletop might feel or look like smooth one, but in general, if we look inside, take a microscope, it's a very rough surface. So when we have a beam of light traveling toward it, after the reflection, it goes in all possible directions. That's what we call diffuse reflection. But what can we do? We can polish it. If it very good polished surface, in that case, the reflection happens in this way. So if you have several beams of light traveling parallel to each other, after the reflection, they remain parallel to each other. And that's what we call a specular reflection. And this is the time when we need to look at it. Come on, come up. So what do I do? That's what I do. All I need is a source of several parallel rays or beams. Like these. If you have a snow in a can, you can actually visualize the lines and hope it's not toxic. It's not. So parallel beams travel away. We place a mirror And that's it. They all remain parallel. This is a plane mirror. So for the plane mirror, technically, we only need to know what's happening to a single ray. And all other behave in the same way. And to describe the behavior of a single ray in this type of a mirror, we have to apply the law, which has a name. The law of reflection, because it's about reflection. The only thing people sometimes forget is the first part of the law. Everybody remembers the second part. The angle of incidence is equal to the angle of reflection. The angle of reflection is equal to the angle of incidence. But people forget about this part. So a mirror is a surface. And in physics, to describe an orientation of a surface, we always use the same vector, which always has the same name, normal. So here we need to use three directions. One direction is described by the ray approaching the mirror. We call it the incident ray. Second direction is supposed to be described by the normal. And the third direction is supposed to be described by the ray moving away from a mirror, and we call it the reflected ray. So, approaching, reflecting. That's it. But the importance of the first part of the law says that when the light is approaching like this, it cannot be reflected like this. Even angles might be the same. This situation can never happen. So that's what we say. This ray, the normal, and the reflected ray should lie in the same plane. And these angles, the angle of reflection and the angle of incidence, are equal to each other. So, how do we form an image? Yeah, we know we use mirrors, we look in the mirror. So what we see is an image of ourselves or other objects. Well, first we need a mirror. And now we just have to apply the law. So let's say we have an object like this. This is a standard representation of an object. So this is the highest point of an object, maybe tip of your head. And this is the mirror. And rays travel, well, let's say, I don't know, it could have been a candle or a bulb, an actual source or reflected source. How do the rays travel? Well, this ray, when it reaches the mirror, should be reflected straight back. This ray, when it reaches the mirror, should be reflected how? Well, we have to apply the law of reflection. So to apply the law of reflection, we must draw the normal to the mirror first. Then we can see the angle of incidence. Then we can take a protractor and measure the angle of reflection, which is supposed to be equal to the same value. And now we can draw the reflected ray. And we can repeat it many, many, many more times. Now, do you think if you, a person with eyes, would walk behind the mirror and would be looking at the object, you would see anything? Does light go through the mirror? No. Well, if it's not specially manufactured, but a normal mirror doesn't transmit light. A normal mirror reflects all the light. So there is no light behind the mirror. Yeah. But when we look at ourselves, we see ourselves kind of behind it. So what's happening? Well, there is an image which is not an actual image. It's imaginary image, but in physics we call it virtual. So there is virtually an image behind the mirror, and we can draw the image and kill the person. And that image, of course, if it is formed by a plane mirror, has exactly the same size, exactly the same orientation, and located at exactly the same distance from the mirror, only behind. So how do we see that? Well, jumping ahead, we use eyes. Without eyes, we couldn't see it. And what is an eye? You know it. It's a lens. So we actually use a second optical device. Without second optical device, that image wouldn't be possible to see. So we go back to this in the future, but for now, all we have to say about this image using the terminology people have developed to describe all possible images. The size of the image is the same as the size of the object. The image is upright, and normally we always place an object upright. In general, we would say the image has the same orientation as the object has. And the image is located at the same distance. In general, could have been closer, further, smaller, inverted, and that will happen in the future. All right, any questions so far? A plane mirror is the easiest optical device. We can use this to figure out, so this is the summary of the properties of the plane mirrors. And one thing I didn't mention yet, this is important. There is a convention and agreement. When an image doesn't really exist in nature, it only exists in our head, a virtual image, we assign a distance from an image to the device to be negative. We always can measure a distance from an object to the mirror, because an object, a mirror, actual things, we can measure it. But if an image doesn't really exist, so everything we say about it is just imaginary, or we say virtual. And to describe this fact, the distance from a virtual image to the mirror set to be negative. Now, when we look in the mirror, again, we, people, look in the mirror. That's a mirror. Let's say this is not you, not me, but your enemy, because it's ugly. What would you see? Well, we know that in general, an image, a virtual image, doesn't really exist unless we start using an additional optical device like an eye. Should have exactly the same size, exactly the same orientation. Almost the same. So, what size of the mirror should we use in order to actually see the complete image? Well, actually we don't have to. Well, you know, if you take a very small mirror and you look in the mirror, you cannot see full you. It's impossible. But if you, in front of a large store window, you can see yourself. So there has to be that critical size of the mirror, which is sufficient. If it's smaller, you cannot see yourself. If it's larger, definitely. So, and turns out now, if we use the law of reflection, it's very easy to figure out the size of that mirror. So first of all, well, that's your eye. So this is where the light comes back after being reflected. If you need to see your feet, you should look Yeah, now a ruler would be handy because we draw straight lines. So this is the actual light ray which gets from your feet to the mirror and then gets reflected. But our brain thinks that light actually comes from that. So this part below this point is not required. It doesn't do anything for you. Same for the top of your head. The light should go from the top of the head and be reflected to reach your eye. But our brain thinks that the light actually travels like this. So this part of the mirror above this point is not required. And you can see, I hope you can see, this is actually, if you're h meter or feet high, this should be equal to a half of it, that's it. Well, this is a half of this, that's a half of that. But you'll also see that this mirror is supposed to be placed at exact height. If you move it higher or lower, so some part of your image disappears. Kind of neat. So you can go to a store and say, I need the mirror which is exactly of my height. Why? Because I don't need any more. I need larger. Well, that's a better picture. Now, we can ask a question, what's going to happen if we bend it? Well, I'm not strong enough, but when I hide, I become much stronger. And see, I bent it. Well, we can understand what should be happening, and we will take a look at it later. But first, we should understand what should be happening by using the law of reflection. So, let's say we cut out a piece of a sphere. Technically, we can have both surfaces to be polished. That's one type of a spherical mirror. That's another type of a spherical mirror. This is what we call concave, cave, something inside. This is what we call convex. And let's say we have a concave mirror. First, this middle point, the top of a mirror, has a special property. The mirror is symmetrical about it. So we can draw a line which is perpendicular to this mirror and travels through this point. And this line has a name, the principal axis. So normally, if you want to analyze what does a mirror do, we place an image somewhere like this. Well, for now, let's just take a look at one point, this point. Bless you. So a ray travels, let's say it travels like this. A ray only now knows, sees, feels this part of a mirror. Only their interaction between light and mirror is happening. So for this ray, this mirror looks like a plane mirror angled at this angle. And for this situation, we can apply again the law of reflection, and the reflected ray should travel like this. Turns out, if this, we call it HO, the height of the object, if this is not very large, much smaller than the size of the mirror, and any other ray which is parallel to the principal axis after the reflection goes practically through the same point. Seeing is believing. Don't be scared. See? After the reflection, there is one point. Well, we can maneuver with the mirror, and we can, of course, move that point in a plane. But if all rays are parallel to the principal axis, this point lies on the principal axis. So this point has a name, a focal point, and a distance from this point to the mirror has a name, focal distance. And let's take a look immediately at the opposite situation. So now, when the mirror is convex, after the reflection, rays diverge. So we also have two different names for mirrors. This mirror also is called a convergent mirror because it converges light rays. When they being reflected, they bend toward the principal axis. But in this situation, they reflected and travel away from the principal axis. We call it a divergence, and so this is divergent mirror. And do you see any light behind the mirror? Of course not. Let be the light. So a focal point, people use capital F or lowercase f, a focal distance, and whether we like it or not, people do not use D or S for the distance. People also use the same letter F for the distance, focal distance. And for a divergent mirror, what should we see? Well, if we have several rays which travel parallel to the principal axis, after the reflection, rays move away from the axis, but not arbitrarily. There is no light behind the mirror, but we always can imagine some kind of a rays behind it. So we use an extensions of actual rays. And of course, if actual rays diverge, the extension in opposite direction should meet somewhere. That's what we call a focal point. But now, of course, we should call it a virtual. Everything which doesn't exist in real life only exists in our mind, we call virtual. And this will be the focal distance. But of course, because it's virtual, we should make it negative. And now there is another geometrical fact which you can derive. It's geometry, you can practice with geometry. The focal distance in both cases has magnitude equal to a half of the radius of a sphere. That's a sphere. It has a radius. We cut out a portion of it, we make it shine, and we make a mirror. And the focal distance will be equal to a half of the radius. Only for a real, for conversion mirror, it's supposed to be positive, so but for a diversion mirror, it's supposed to be negative. So, pictures, slides, the summary, diagrams. It's physics. You can't escape drawing pictures. And for mirrors, we can draw 4 possible diagrams. Case number 1. So diagrams depend on the type of a mirror and on the location of an object. So, of course, we start from a converging mirror. Case number 1. The principal axis. We know it has a focal point. We know it's been cut out of a sphere. That's the center of that sphere. And we know that the radius equals doubled focal point. So technically we have 3 possible locations of the object. We can place it behind the center of the sphere, between the center of the focal point, or between the focal point and the mirror. 3 cases. And for each case, so let's say this is my object. This is what we call the object distance. Always positive, because an object is always a real thing. This is what we call the height, the size of the object. And now we need rays. Well, we know that every ray which travels parallel to the principal axis after the reflection should travel through the focal point. But now there is another very, very convenient ray, second ray, which actually goes toward the top of the mirror. Because for that ray, the mirror is just flat, plane mirror, which means for that ray, it has to be reflected at the same angle. These 2 rays cross each other here. So this location represents the image of this point. And of course, we can repeat the same procedure for all points of an object, and we will get images of all points. And that will be the image of the whole object. We call it an image. And that's what we call the image distance. Because an image is an actual thing, what does it mean? It means that I can actually take a piece of paper, use it as a screen, place it here, look at it, and see it. That's what that word real means. We can see it without using lens. We just need a screen. So for a real thing, a real image, distance is positive. And I'm going to write it right now. You see a lot of triangles here. A lot of triangles. Yeah. O, A, P. B, D, P. This angle equal to that angle. And you can use a geometry and you can actually derive that these variables related by this equation, geometry, and exercise. This equation has a name, mirror equation. So if we know any 2 of these variables, we can calculate the 3rd one. Now, we also can see that the image is inverted. To demonstrate that fact, we assign the size of the image to be negative. So everything what is upright is positive. Everything which is downward is negative. What else we can see? We see that an image actually is smaller than the object. To demonstrate this fact, we introduce a quantity which we call magnification. The magnitude of the magnification equals this ratio. For now, that's enough. And this is just a definition of what magnification is. The actual value of magnification depends on the actual value of the height of the image. So it could be negative or positive. The magnification could be greater than 1 or less than 1. We call it magnification in any case, just a name. Now, quickly, second possible case. You should be more accurate than I am. It's supposed to be. It's actually easier to start from drawing the axis first, and then you can draw a mirror. So a half of a mirror above, a half of a mirror below, focal point, center of the sphere, and now we can place an object here. So rays. The ray which is parallel to the principal axis after the reflection must travel through the focal point, no doubts. The ray which goes to the top of the mirror must be reflected at the same angle. That's why using a ruler and protractor kind of handy. Lines must be straight, not bent, those rays. So well, more or less. That is the image. Okay. Names the same: object distance, image distance, the height of the object, the height of an image. So all properties of an image very similar to case number 1. The only difference is the image now is larger. So everything remains the same as before, same equation, same definitions. And case number 3, again, principal axis, mirror, focal point, central, and I want to place my object here now. This is my object. So still, the ray which traveling parallel to the principal axis, I don't know how many times did I say, but still must travel through the focal point. The ray which travels toward the top of the mirror after the reflection should have the same angle. Do they converge? No. So that's a general rule. For this situation, there is a general rule. When rays do not converge, we should draw extensions of those rays behind the mirror, because those will converge. So when they converge, we have an image, but there is no light behind a mirror, which means this is a virtual image. And for this image, the height is supposed to be positive because it's upright. The magnification will be greater than 1. But again, the general rule is that an image distance of a virtual image must be set to a negative number. The object distance is always positive. We can use the same equation. But in this equation, we have now 2 positive numbers and 1 negative number. And finally, the case number 4, what's left is only one type of a mirror. And for this type of a mirror, the distance between the object and the mirror doesn't matter. That's why we have only one case. The result will be always the same. We place an object. From this object, we can draw two rays. This is supposed to travel how? Well, in general, we always have three options. But in general, only one option is correct. For the plane mirror, this arrow would be correct. For the concave conversion mirror, this arrow would be correct. But for the diversion mirror, these two arrows are wrong. And this arrow, well, technically, we don't know. We know it bends away. But in order to draw the exact beam, we need to see the focal point. But now that's a virtual focal point. So we have to say, this is our point. And extensions should go through that point. So, okay, good fit. That's the first extension. Now, the beam reflected by the top of the mirror still reflects at the same angle. And the extension now behind the mirror shows the location and the size of a virtual image, an object, an image, height of an object, height of an image. Upright means positive. Smaller than the object is, so the magnification will have magnitude less than 1. This is the object distance. This is the image distance. Always positive. For a virtual image negative, the same equation can be used again. But in this equation, now we have two negative numbers, positive, negative. What else should be negative? Virtual focal point, this is supposed to be negative number. That's where people make mistakes most commonly. They forget what's positive, what's negative. All right, thank you very much. We are done. I, of course, have slides with all these cases and equations. And technically, if I open the homework, you can start doing it. So probably I'm going to open the homework anyway, so. No, I will use it. I will use it next week. Just take it, but you can put it with other speaker.